So this tutorials will be covering the compute architectural solution targeting the AI workload. And the speaker is Bharat. Uh, He's a senior principal engineer and director of engineering, Havana Labs at Intel. He has worked more than 24 years in this computer architecture, AI/ML hardware, CPU, and VLSI design. He has incubated multiple ideas and led a design of AI and ML compute for data center and servers. He has received the Intel highest award, IAA, we call. And Bharat has a master's in computer engineering from University of Delaware, US, and bachelors from Osmania University. He is a great sports lover to keep him physically fit all the time. And welcome, Bharat.
Thank you, Vishwajit. We're going to talk for the next hour and a half on what is this new rave about SoC architectures for the AI compute, why we need a SoC or dedicated SoCs for AI compute, and what is the business opportunity. So we will go into that in detail. So just in terms of the overall agenda for the next hour and a half, I'll cover what is the AI compute, the difference between training and inference, what are the different data types that AI compute employs for different workloads or for training or inference use case. What does the compute engine or the compute core for the AI look like? What are its key characteristics and what determines the key performance and performance per watt improvement that we must and that these solutions deliver? The sparsity and inherent in the machine learning workloads or the neural network topologies, and how do we take advantage of that? The memory and cache organization for the SoC for AI. And lastly, the scale out architecture when we are targeting very large models or reduced time to train. So we'll go over this. I will introduce some of this terminology as well and talk in detail on these topics. Okay. So what is AI and why and what is this all rave about that we are hearing lately? So AI has been around for a long time. It is 40 years old or something like that, and there was an AI winter for a long period of time where not much activity in terms of the research or commercial. In around 2012 or so, there was a breakthrough moment in AI with the advent of this gradient descent and an ability for neural networks to learn on their own, provided we give them a lot of training data. And this opened up a plethora of opportunities. But that field that we are referring to is really the deep learning field, which is the neural network organized as deep layers, and hence the term deep learning. Machine learning is a superset of that, which employs not just the deep learning, but even more statistical learning models. And this overall field is characterized as the AI, as you see these concentric circles, to just give you an idea about what all these terms mean. Now, within the deep learning, by the way, the talk's focus will be all on deep learning predominantly, and the compute for the deep learning, as the compute demand is exponentially growing for the field of deep learning. The deep learning itself is classified further into supervised learning or unsupervised learning or reinforcement learning. Supervised learning is when you have labeled data and you train the neural network with that labeled data. So there is the supervision provided by the human intelligence to label all the data, and then the deep learning learns the weights based on the labeled data, and then can predict any future new data that comes in. Unsupervised learning is when you don't have labeling to the data, but the deep learning can still recognize the similarities or differences in the patterns of the data and can group them into different subsets or classify them. And this is the field of unsupervised learning, quite a bit of research going on in there. And reinforcement learning is when you already have a trained data and you are reinforcing with more new data to fine tune your training. So these are all the different approaches that deep learning is taking. And in terms of the use cases, it's bound by our imagination, whether it is use cases in the image recognition, object detection, natural language processing, speech processing, recommendations, security, medical. It's just the use cases of the deep learning are proliferating in every field. So what does this mean? So what does this mean and why now? I mean, why so much interest in AI now, other than the fact that we figured out a very compelling way to train the neural networks? There is a data deluge in terms of the data being generated by the different users on the internet or all the different devices that we use, whether it is your smart cars or medical data or your travel data. And all of this data is going unprocessed, or there is a lot more learnings to be had from this data to derive business intelligence. And this is where AI comes in. The AI algorithms can really bring insights from this data, whether it is business intelligence or operational or security, you name it, and can be used to improve the bottom line of different services or the businesses that are employing the use of the AI. So this sets up the stage for the explosion in the growth of AI in terms of both the data that we process and the amount of compute that is required to bring smart decisions out of this data. So now getting into what does AI or deep learning and how do we get all this intelligence? So I show here a very generic or a simplified object classification example to illustrate the concept and the different mechanisms that that are used by the deep learning networks. So at the input, you have a raw image, and you perform. By the way, this is an example of a convolutional neural network, and then there are different flavors of different neural networks. But I want to use this to set the stage for what is the kind of compute and the different operations required in the deep learning topologies. So you perform convolutions on this neural network, on this input image, and you generate what are called as the feature maps. For each different filter, there is one output feature map. So if you see in the con1 over here, there are all these different feature maps, each one generated using a different filter. And in the picture over here, I show what is the kind of operation being done to generate that feature map. So you have a filter and you move this filter all over the image. And for each position of the filter, you generate an output by multiply accumulate operations. This can be transformed into matrix multiplication operations as well. So it boils down to convolution operations or matrix multiplication operations to generate the feature maps. The feature maps themselves go through something called as subsampling or pooling, where you look at a block of data in the feature map and identify the average value or the max value of that to represent that block of data. This is to reduce the size of the feature maps as we are going deeper into the topology. The feature maps themselves then go through something called as a nonlinear activation, or I show an example here of ReLU, which is a rectified linear unit. There are different types of nonlinear activations as well. And this tends to remove the negative values or the values below a certain threshold so that we can focus on the key features as these feature maps progress in the deep learning topology. Once we are done with all the convolution layers, that is called the feature extraction phase of the neural network, then you go into something called as the classification, which is the right-hand side of the neural network. And in the classification stage, we do something called as a fully connected layer. Fully connected layer is nothing but a matrix of pixels are multiplied with weights to perform to classify them into all the labeled data. So in this fully connected layer, the inputs are the image pixels, and the output here is the different labels of the data for which we are doing the training or the inference. So this label, these are the labels which predict what the input image was. This fully connected layer in terms of the compute is nothing but a matrix on the left-hand side being multiplied to generate a vector as an output. So it's a matrix vector compute. And then you do a softmax on it, which is a yet another nonlinear operation to determine the probability of the object detection. Now, this deep learning models need to be trained, and then they are used for inferencing the new data. The training is a two-step process where you do a forward propagation of through the network, and you see what the prediction is, but you have the labeled data so you can identify what is the error in the prediction, and then you back propagate the error through the different layers of the network to identify the error in the learned weights and adjust the weights. And this operation is done iteratively over all the images or the data. In this case, I'm taking an example of the images that you have in your training data set. And at the end of it, you continue to update the model weights. When the model weight updates go down below a certain threshold that you are not updating by larger than that threshold, then you say the model has converged and you have learned the weights and you have a learned network. Once you have a learned network, then you can deploy that for inference, where you can bring in any non-learned image or any non-labeled data. You pass that image or the data through the network and you get your prediction. And this is where you can go through tons and tons of data for all kinds of use cases. In terms of training and inference and its impact on the SoC or the architectures that we're going to delve into, the training has multiple passes, and the backward pass is twice as much compute heavy as the forward pass. So the training overall tends to be about 3x more compute than inference. We can batch these images and send batches of images through the network at a time. This helps do more parallel processing and use our compute more efficiently. The model update or the weight updates tend to become smaller and smaller as you tend to progress in the training. And so you need a very high precision data type for the training. So you will see that typically the data type used is floating point 32, which provides a large range and a large and a very fine precision so that we don't lose the weight updates. Once we get into inference, the inference is much more latency critical, but because as you get images, the user clicks, we need to go through classifying the data in a very certain response time expected by the end level service level agreements. So inference tends to be latency critical. So you tend to operate inference on smaller batches, not on very big batch. But then again, the compute on inference is also smaller. You can take advantage of sparsity to bring in more power efficiency. You can use lower precision arithmetic for inference because the neural network by definition are more sparse. They are more error tolerant. And so losing certain precision when you're doing inference it tends to be acceptable. So this is the setting the stage for the different requirements for the training and and the inference as we dig into the SoC architecture. So talking about the AI architectures, there are many different AI solutions in the marketplace. There is the incumbent CPU, and the CPUs are going through their own instruction set updates, new instructions being added to the CPU to accelerate AI compute. There is the GPU, which are inherently parallel compute, but they are being augmented with the systolic array. We'll dig into what systolic arrays are, to add the kind of compute required for AI. CPUs and GPUs are more general purpose solutions. CPUs are more general, GPUs are specific, but still quite a bit general and have a very evolved programming model. A new class of SoC architectures are coming up, which is the SoCs custom built for AI, where they try to take advantage of all the AI compute and targeting AI workloads. These tend to be much more efficient than CPUs and GPUs, both in terms of power and cost, but are again targeted only for AI. There is the wafer level compute, which is a bold new experiment where you don't package the AI chips or chips in their standard packaging, but you keep them all on wafer and connect them using very high speed interconnect. And this helps with very large compute in terms of scaling the compute for AI. We are not going to talk too much onto the wafer chips. This is much more of a bold experiment, but this is another experiment being tried out by a startup called Cerebras. The FPGAs are used opportunistically for AI compute, where you can have targeted topologies baked into your FPGA, which has quick deployment, can provide efficiency over CPU and GPU, but have to be reprogrammed for each new topology. There is another class of solutions emerging called neuromorphic. I think the previous speaker also talked about it a bit more, which are more brain inspired, exactly how neuron work. This is much more of an evolving field. For today's talk, I will be focusing on the AI accelerator SoC, which is the custom SoCs, which are gaining a lot more traction in the industry, both from a business and commercial point of view, as well as from an academic point of view. Looking into the AI SoC architecture, it doesn't look very different from the SoC architectures that you see for a lot of the different use cases. You have the AI compute cores. Each solution brings in different number of computes or the size of the compute core as well. Whether you have 8 cores or 16 cores or even thousands of cores, depending on the size of your core. They are all interconnected using an on-chip network on chip and a last level cache to share data among them. They are connected to a memory subsystem to get bandwidth and data from your DRAM or HBM, the type of memory that you choose to have. You have connection to the host CPU, typically over a PCIe endpoint. There are other solutions being looked at also, but PCIe endpoint-based solution is the most popular solution being used today by the AI accelerators. Opportunistically or by on a need basis, you have video coders to reduce the bandwidth for the images that you're bringing in or the images that you're streaming out after classification. So you have video codec within the SoC and the scale out links. So these are the link to connect multiple such SoCs together for addressing very large compute needs, especially the recent compute for networks like GPT-3, which has trillions of parameters. Training them on a single SoC is untenable. So you scale out the solution, connect thousands of these SoCs together and train the whole neural network model on a scaled out architecture. And we will talk about the scale out architecture as well. Okay. So before we get into the compute architectures, let's talk a little bit about the data types. The data types are very critical to get it right for an AI SoC. We have multiple different data types starting from FP32, which is the standard or the most widely used for training. It is a very standard data types available in all CPUs and GPUs, and this availability makes it very easy for researchers to use this data type for training. It has a very large range, and with very high precision. I show the details on the range and the precision that you can get, in the order of 10 power 38 for the range, and to the seventh decimal in terms of the precision. But it is costly. It is 32 bits of data for every element, and the each operation is also power and area intensive. So the researchers have been looking at lower precision arithmetic for neural network, because the neural network tend to be very tolerant to errors. So there are different approaches for lower precision, whether it is floating point 16 or bfloat 16. Each comes with a different flavor of exponent and mantissa. Floating point 16 has 5 bits of exponent and 10 bits of mantissa. bfloat 16 has 8 bits of exponent, same as the FP32, but the reduced mantissa is only 7 bits. So you get the same range, but lower precision. And it is easy to interoperate between bfloat 16 and FP32, where you can do certain layers in high precision where you need it, and certain layers in lower precision of bfloat 16. And this hybrid mode of working with different precision is also being actively used in the SoC architectures. So for any SoC considering it, you need to think of supporting multiple data types and interoperating between the data types so that you can get the best of accuracy and performance or power. TensorFlow 32 is another data type, which is the union of floating point 16 and bfloat 16, and can interoperate with the bfloat 16 and floating point 32 very easily. Gives you the same range as bfloat 16 and the same mantissa as floating point 16. Floating point arithmetic tends to be costly. So there is the integer arithmetic, which is integer 32 is a standard integer used in all programming languages. Integer 16, again, a standard integer used in all programming languages. Integer 8, which is an 8-bit integer, which reduces the range significantly, but there are ways to deal with it. Integer 8 tends to be very, very power efficient, very, very bandwidth efficient. So it is used a lot in inference workloads, not so much for training, because for training, you need a lot more precision and range. So when you're using integer 8, you have to quantize the data where you have originally trained the data in bfloat 16 or FP32. you have to quantize the data to integer 8. And there are different quantization schemes. So some of the quantization schemes that we will deal with here are dynamic fixed point, symmetric low precision, and asymmetric low precision. Each one has a different cost of quantizing the data and shares and trades off for the accuracy, or how precise you can use your 8 bits of data. In dynamic fixed point, you basically map the range of your input data to the 256 range that you have in your integer 8, which is from -128 to +128. And you use a simple shift, so you provide the data in multiples of 2 power n. In symmetric low P, you add to the cost a little bit, where you do one more multiplication to take the input data range to map it to the max value that is supported in the integer 8. But the data is still symmetric with the midpoint being 0. And this gives you the better utilization of your 8 bits of data. In this, the green part is the used range of the 8 bit of data, and the red part is the unused range of the data. So you can see, as we are increasing the cost of transforming the data from dynamic fixed point to symmetric low precision, we get better utilization of the 8 bits that we spend to represent the data. We still have some inefficiencies left. So this is where the asymmetric low P comes in, where we add a additive component. So you do not just a multiplication, but add a bias, so that you can represent the data even if it is asymmetric. So if you see the original data is going from -3.1 to 5.2, this can be represented in the full range, because you normalize the range. You represent 0 for -3.1, and that is the bias that you keep. So all these transformations need to be done on the fly, and the architectures use different quantization schemes depending on the accuracy they target. Okay, so once we have the quantization scheme understood, we can now start to design our AI compute node. So what does an AI compute node look like? It needs to have a matrix multiplication or a convolution engine to do the large amount of compute. As we saw originally, the matrix multiplication or the convolution operations are typically multiply, add, multiply and add operations, which you continue to accumulate over a period of time. So you have a big compute grid. This is where the bulk of your compute happens as far as the neural network is concerned. However, the neural network is not just the matrix multiplication operations, but also other operations like subsampling or pooling or data normalization or nonlinear compute like softmax or other operations, for which you need a programmable core. So you see different SoC architectures using different vector core, but almost all the solutions employ some kind of a vector core which is programmable, so that as you go and deploy this and new topologies come up or new compute operations come up, you can map them to your vector core. So this is a rich set of libraries are provided for the vector cores typically, and this forms the next set of compute provided in the compute node. There is the other part which is called the post-processing, which is when you are computing layers of neural network and going from one layer to the next layer, you can do post-processing on before streaming the data out for the next layer of processing, like ReLU or subsampling or pooling. Some of these operations can be done in the post-processing. And this avoids one read and write to the memory, because you are streaming out the data, and while you're streaming out, you are processing the data for this additional operations. This post processing can be significant in terms of improving your overall efficiency, because it reduces the data bandwidth that you need to provide. And the data bandwidth tends to be a limiting factor in your SoC design. Once the data is post processed, you can put the data in your cached or even stream out of your compute node to your next higher level cache or even to main memory. You have data and control fabric connecting your vector core, your compute grid, the 2D compute grid, and your cache or the SRAM to among each other. You have one controller. The controller has the knowledge of your compute graph or the different layers that you are trying to process, and it sequences the operations between your compute grid, your vector core, or moving the data in and out of your cache using the DMA. So this controller is dispatching the tasks to the different components that we see in the compute core. And finally, you have the MMU, which provides address translation for different AI cores to be communicated among each that talk among each other or between the SoC and your host, which you are connected to over PCIe. So this is the typical components that you see in your compute node. Now, the biggest piece of the compute node is your systolic array or the matrix multiplication engine, which consists of a two-dimensional grid of laid out processing elements. Each processing element is doing a matrix operation called multiply and add operation, and then passing on the data to the next PE to take it forward. These compute grids are typically fed by an input memory or an activation memory from one side, a weights memory. This is the weights of the neural network that are learned, and then the outputs, which are the output that are fed to the subsequent layers or to the final classification if you are in the last layer of the compute. The systolic array is a popular approach used. It provides significant advantages over some of the other approaches in terms of the compute grid size and the power and performance. In the systolic array, you have activations flowing down. By the way, this is a way of doing a systolic. There are multiple ways of doing a systolic. The concept is similar. So take this with as saying more conceptual. Every SoC or research group may have a slightly different implementation of it. So you have activations which are coming down. They are acted upon in a PE, and the output of this PE goes to the next, which is acted upon by the next set of weights to take the compute forward, which is accumulated and then going forward. So as the data traverses down a column of processing elements here, it is doing the matrix multiplication operation or the convolution operations, and a final result is stored in the output memory. Each column is working on a different piece of data, but the operations are the same. And the weights from the weights memory are being broadcasted to each row of the compute. So every row has a different weight, but each row has the same weights, just acting on different data. So this gives you the cross of the weights and the input data. And for the data movement corresponding to n inputs and n outputs, your compute grid has n square elements. So your grid size is n square for a total bandwidth requirement of 2n for the inputs. And then, of course, you are streaming out your outputs to be processed for the subsequent layer. If you look at the data movement here, each of the data movement is point to point, from input to the first PE, from first PE to the second PE, and so on. So these are short communications, which are very handy when you want to scale the operations for a very high frequency. They are low power and are bandwidth efficient, because you need only 2n bandwidth for a n square compute. Okay. So now I will dig into how exactly is the matrix operation being done on the systolic array. The example I took here is a simple example of a very square matrix, which is broken up into 4 blocks. The input matrix has 4 blocks, and the weight matrix also has 4 blocks. And we're going to feed each block at a time to the compute grid. The size of the block can vary depending on your design choice, whether it is dictated by the size of your weight memory or the size of your compute grid. So you bring in 1 block of the weights, 1 block of the inputs, you do the matrix multiplication on this block of data, and you stream out that data in and store it in your output memory, which is also part of your compute grid. Once done, you move on to the next data, which is the next block of weights data, next block of input data. You do again the matrix multiplication, and you add that to the previous result. So this is an example of output stationary, where you stream the inputs, but the output is stationary, and you accumulate on top of the output. Moving on, you bring in yet another new set of data. You do again the multiplication, and you stream out the output, and then you bring in more data and accumulate on top. You perform these operations iteratively until you are done with the complete matrix multiplication operation. Now, depending on the matrix size and the memory sizes that you have available, there are different loop unrolling strategies. For example, in this example, we updated the output data first before creating new output data. So this was output stationary. Similarly, you can say, I am going to use the input data of the weights block 1 with the input data 1, as well as input data 2, both before I throw away the weights and bring in new set of weights. So this would be weight stationary. Similarly, you can do input stationary, and you may want to keep this dynamic also, because this may be dictated by your matrix topologies, which will vary depending on the workload. So the modern or more sophisticated approaches, you will see that the loop unrolling in matrix multiplication is kept flexible, dynamic, and it is done based on either the size of the compute that you need to do, or the size of the memories that you have, or the size of the compute grid that you have. This is not this is for the memories of one hierarchy. How about higher hierarchy? For example, you have last level cache. So you can have even more sophisticated loops, where you do this loop unrolling strategy for your local memory first, and then you repeat the process where you might employ a different strategy or different sizes of the blocks for the next higher level memory. And you get a very sophisticated loop unrolling strategy, which is where you get your performance benefit and performance per watt benefit. Okay, so what dictates the size of the compute grid? Earlier we talked about that for compute grid of size n square, the data movement is 2n. So as you increase the size of n, your compute increases quadratically because of the equation, 2n of bandwidth to n square compute. And the data movement tends to be a large piece of your performance cost or your power cost. So it is more beneficial in performance per watt and also to be able to provide larger compute at lower bandwidths to have a very large compute grid. But then we need to map that with the utilization of the machine. If you have a very large compute grid, but your matrices are small, then you cannot use all the available compute, and then you have reduced utilization of the machine. So this is a trade-off that researchers use to size their compute properly, whether it is for training or inference. For training, you can batch more data, so you can tend to put bigger compute grids. For inference, the latency is more critical, so you may not be able to batch a lot of data, and hence the compute grids may be a little smaller. So that's the other trade-off in terms of the grid size, bandwidth, and power. Moving on to the memory organization, this is a very routine depiction of the date of the memory organization on the CPU, the GPU. On the CPU, you have the L1 cache, the L2 cache, and the L3 cache. On the GPUs, you have your register file, texture cache, your L2 cache, and so on. The accelerators employ a reasonably simple memory scheme where they provide more of a buffer, which is managed by explicit movement of data by the programmer into the buffer and out of the buffer, which is called a software managed buffer. However, the software managed buffer comes with a high software complexity because the user program needs to explicitly manage the data in and out, but it gives you a very good control over the block of data that is always present as you are doing the loop unrolling strategies for your matrix multiplication or other operations. However, like we said, it comes with higher complexity. A more sophisticated architecture for the accelerators lately is employing a hardware managed cache. It comes with a little bit extra cost of maintaining the tags and the coherency, but it simplifies the software programming model because it doesn't need to be guaranteed that the data is there. You can manage to pin the data in a cache, and even if the data gets kicked out, it is still functional because the coherency will make sure that the data is latest and functional. Okay. So in terms of the data organization, the loop unrolling strategy can take advantage of different hierarchy of caching. You can have a caching within the PE grid, within your compute grid, and then at the SoC. And you see typically architectures using all three caching mechanism and the loop unrolling, doing this hierarchically for all three different caching mechanisms. You have the local memory connected to the PE grid, and then you have the shared memory connected to with a central bus among all the different AI cores. In terms of your memory organization, you can say the local memory is maybe an SRAM, not necessarily a cache, whereas the shared memory is a cache because within the local PE, the loop unrolling strategy is more defined, so you can take advantage of the shared memory or reduce your cost of instantiating the memory. When you go to between AI compute cores where you might be parallelizing using different approaches, you may want to have more of a hardware managed cache to keep your software complexity low. But again, these are different trade-offs in terms of software complexity and hardware cost. So why do we care about these different hierarchies of data? This is a data collected from the, MIT research in terms of the energy cost for the data within your compute grid, normalized to data within your compute grid or the register file. So as you do your L1 cache, the energy cost is 2x. As you go to next level cache, your energy cost is 6x. And when you go to a DRAM, the energy cost is 200x. And you definitely want to reduce the overall energy cost, because performance per watt is a significant metric which limits the performance of your overall SoC. So you want to organize the data in different hierarchies to get the most optimal energy cost. Talking about energy cost and bandwidth, there is inherent property in the neural networks called sparsity of data, whether it is sparsity on activations or sparsity on weights. Neural networks tends to be very error tolerant and sparse. In the activations, we saw that you have ReLU or other operations which zero out the data below certain threshold. So you tend to have large amounts of zero data in your activations. And when you are going from one layer of compute to the next layer of compute, you want to optimize your data movement, your compute, so that you are not using the zero in your compute, because zero multiplied with anything doesn't add to any value. So the ReLU or the activations tend to be the source of sparsity in your input data or your activation data. The other source of sparsity is your weight matrix. You can train the data such that the trained data below certain value is zeroed out. It is called quantization aware training or sparsity aware training. And this trained data, once made into sparse, can improve again your performance, reduce your power, and improve the performance of the SoC overall. It comes with potentially accuracy loss, because you have zeroed out certain low threshold data, and so it's a trade-off between your accuracy and the sparsity that you can that you want to have in your system. So how do we take advantage of this sparsity? First of all, the most simplest one is, as you encounter zeros, clock gate your PEs or processing elements. And once you do the clock gating, you save the power that you would have burned multiplying with that zero. But that is not all. You can compress the data, where you remove the zeros and you bring only the non-zero data into your compute grid. This reduces the bandwidth requirement and also reduces the power for moving the data. So this is clock gating plus the compression. But you can continue on that, where you have non-zero data and you want to eliminate the non-zero data from your compute altogether, so you can accelerate your compute as well. So you get the advantage of power and performance, not just from the performance of reducing the bandwidth, but also reducing the performance requirement, and hence improving your compute grid utilization. So these are all the different techniques that the sparsity can employ. There are different types of sparsity that architectures work with. There is the fine-grained sparsity, where the zeros can be anywhere in your data. This is the best for your accuracy, but it is difficult to take advantage in your hardware because of the unpredictable nature of the zero data because you are trying to do the broadcasting of the weights and the inputs coming in, going through a compute grid. This non-deterministic zero behavior tends to have some cost in your hardware to take advantage of. So we look at doing a little bit more regularization of this sparse data, and that's called block sparsity, where you tend to say a particular row of data is zero or a particular column of data is zero. Of course, it reduces the opportunity that you have in terms of the sparsity, but it is very easy to use for a very little hardware cost, and you get some performance and power advantage. You can continue down this path to say a mixture of fine-grained and block sparsity, where you have blocks of data, but you have fine-grained sparsity within the blocks of the data, which is a good trade-off between your compute complexity and accuracy loss. And you will see some of the modern architectures employing this fine-grained block sparsity. So what does the sparse compute look like? So bringing back the PE grid here, where I'm showing a row of PE, but that is applicable for multiple rows of the PE. And you have the weights or the A matrix broadcasting the weights on all the PEs, and the different columns of your input data coming in into the PE from the top. In this, I have taken an example of the input data being sparse, and you have the knowledge of all the zeros that you removed from this input data. And that zero information is used to skip over the A matrix data that needs to be broadcasted to all the processing elements. So the weights corresponding to this zero does not need to be sent to the PEs, because we don't have the zero coming in from the input data. So we can skip over that compute, bring in the next data, input data, and the next weight, and we can accelerate the compute through the processing elements. Of course, there is a cost of skipping over the input data and muxing the right set of weights into the processing elements. Each processing element may see a different level of sparsity, and so the broadcasting need to be maintained in a rolling window, and this also adds to the cost, but improves your compute efficiency. And this needs to be balanced to say what is the cost you're willing to pay for what amount of a compute acceleration. The higher the sparsity, the more efficient or more payback in terms of the paid hardware cost for the sparse workloads. Typically about, if you have less than 30% sparsity, this approach doesn't make sense. But as you go into higher sparsity, you can accelerate the compute significantly. Okay. Getting into the next topic, the scale-out architecture. So for very large neural networks, which cannot be practically trained on a single SoC, we need to string together these SoCs in a grid of compute, and then run the network over the complete system. There are different approaches of communication when you construct a very large system using multiple SoCs put together. I show some of the examples here, and then there are more hybrid examples than what are shown here, but want to get into the basics of the scale-out architectures. There is the all reduce, where all the independent nodes do compute and then communicate to a central node. which aggregates all the updates and then distributes the data back to all the worker nodes for the next iteration of the compute. So this is all reduced. Then there is all to all, where each node is communicating with every node so that they get the data from all the nodes so that they can do the aggregation at each node independently and then move on to the next iteration of the compute. All to all tends to have higher bandwidth requirements because everybody needs to talk to everybody, but then there is no downtime in between of gathering all the data, doing the accumulation, and then spreading it out. So how can we optimize this all-to-all data? So let's say there are n layers in the neural network, and there are n compute nodes or n SoCs in your system. We can do something called as reduce scatter, where you send the data for one layer to one SoC. So you see the data from all the SoCs, the red data from all the SoCs coming to SoC1, the blue data from all the SoCs going to SoC2, and the green data going to SoC3, and so on and so forth, such that you are sending only 1/nth data from every SoC to every other SoC, such that all of them can participate in updating the weights for that layer. And once they have done the updates, they broadcast that to the remaining SoCs, the n-1 SoCs in the system. So this tends to perform better than all reduce or all to all, but requires splitting up the network communication in terms of layers. And you see all kinds of hybrid approaches being used in the true scale-out architecture so that you get more linear scaling as you add more nodes to your compute. So how does the parallelization of the data work? There are two popular approaches called data parallel and model parallel, and then the hybrid schemes of where you do the data parallel and where you do the model parallel. What is data parallel? In data parallel, each machine is a column. Each column here is a machine, and this is the progression of time. You are doing the same compute on all the machines, but different data. So as the time progresses, you are doing, layer 1, layer 2, layer 3, all the way to layer n, all of the layers of a topology in a single machine, and all the machines are doing the exact same model or the exact same topology, but on a different input data. So this is called data parallel because the data is parallelized across different machines. This is a very popular approach because it is very simple to do. You can say image 1, image 2, or image 1 through 10, you can batch and send to one machine, image 11 through 20, and so on and so forth on different machines. The software complexity is low, and it gives a good scaling. Not perfect, but gives a pretty decent scaling. The downside of this is each machine needs to store the full network topology. So it is not very friendly when you have a very large network because it tends to require then a very large amount of storage. So what is the other approach? The other approach is model parallel, where you do different compute in each machine. So you have I have some bug here in the first column, so I'm going to use the second column. In the second column, each machine is doing layer 1, 2, 3 different layers at a time. The data is going from machine 1 to machine 2 to machine n all the way. This way, the data is going from one machine to the other, but each machine is processing only one layer, not different layers, because machine one is going to process layer one, machine two is going to process layer two, and the last machine is going to process the last layer. So you are parallelizing the model, but the data is flowing through all the machines. So this tends to require less storage, but then there is more data movement as you uh, progress from one machine to the next machine, and the compute is staggered. So this is the model parallelism, and then you can do model parallelism plus data parallelism in different uh, blocks of data, and more hybrid parallelism schemes are used in the modern architectures. So with that, I have come to the end of the topic, where we have covered all the way from the compute grid to how to put together a very large architecture of a system for many different SoCs to address the large compute needs for very large networks or for very short training time. Okay, so now maybe we can open it up for more Q&A.
Thanks, Bharat. Very insightful, discussions, and I thoroughly enjoyed. I'm sure the team here enjoyed as well. So a couple of questions, and a lot of questions are in the post, but I'll go through and in a consolidated manner for some of them. Well, question one, I think this is very interesting one. The wafer level AI SoC, you have seen a lot of good amount of activity going into that field. How do you see the space is going, and what really the academia and industry need to do in this space so that everybody in the world get their fair share of compute need and actually can help the entire society?
Okay, very good question. So the wafer level is you can have a single SoC, you can put together a few multiple SoCs together, or you can put a complete wafer together. When you put a complete wafer together, you get a very large amount of compute in a single piece of silicon, but it comes with its own complexity of how do you deliver power, how do you cool it, the mechanical integrity, and there is quite a bit of work being done to solve this problem. But not just the problems that need to be addressed for the wafer level, but does every solution need that much of compute? And if not, you need a little bit more modular approach also. So a wafer level is good for extreme high levels of compute, especially like if you're talking about GPT-3 or things like that, where it can be quite attractive, but it may not be so attractive if you're talking about compute at the edge or smaller topologies or incremental training where you don't have to go through the complete data set every time. So it's a trade-off. It's a not one solution fit all. It has its set of complexity which need to be addressed, and it has its use case which is not universal.
Thanks a lot, Bharat. Yes, this is actually a very challenging area, and there are a few companies already has come out with the proposals and stuff. It looks that maybe a supercomputer or computing platform we can build inside one tiny apartment in future. It doesn't need a huge space, and there are a lot of opportunities in that space. So in that context, Bharat, right, how do you see this if we make so many multiple SoC in a wafer and then try to interconnect them? Are there any standardizing efforts going on to standardize the protocol of communications between the multiple SoC to get the best in class performance, as well as there could be a lot of innovations and the whole industry can focus on. If you can put some insight into that.
Yeah. So yes, there is a effort going on to standardize so that we can um, both standardize the connection from the SoC to the host, and also for the SoCs to connect among each other. Excuse me. CXL is one such approach from Intel that I'm aware of, which is a open protocol for communication data coherently or with very high bandwidth among chips. And there are other approaches being taken by other SoCs also. A lot of people are doing custom approaches, but I envision this getting a little bit more standardization as more people adopt, the AI solutions or ability to string together multiple SoCs for a larger problem solution.
Yeah, thanks a lot, Bharat. The another question, which is basically, let's say somebody wants to really write an SoC or AI SoC from scratch. What are the key challenges they need to think through, or in other words, what kind of a tool the students or will be doing the research they can use to find out the throughput, performance, power, and then whether the SoC will be giving the necessary acceleration. What kind of framework the budding researchers can use?
Okay, yeah, very interesting question. So it starts with the workload. You need to have some target workload that you use to understand, and there are benchmarks also. You can use some of the benchmark workloads. You have to size your compute grid accordingly. You have to size the bandwidth, and depending on the size of the compute grid and the caches that you provide and the size of the cache that you provide in your SoC, you need to size your memory bandwidth. And these three things together provide you an idea about what kind of overall acceleration or amount of compute that you can see for the given workload. You need to simulate this to see, depending on your modeling of the different components of the SoC, to make sure that you are in fact getting the performance benefit, the performance that you are targeting. And your post-processing elements, your caching, your size of the compute grid, size of the amount of memory bandwidth, the target workload, and last but not least, the software complexity of how you orchestrate, scheduling the tasks to all the different components in the SoC. And you might want to think about accelerating the scheduling of the tasks also, so that you don't get bogged down by the control overhead in the SoC. So these are all the different challenges that a researcher has to optimize and address for a very optimal SoC solution, which is what we went over in the different sections of the talk.
Very good one, Bharat. Again, the another questions. I think a lot of momentum is now getting created in the ecosystem about the RISC-V architecture, and which is basically an open kind of a standard where the people can actually write their own adds-on utility to enhance the overall throughput. Now, the question is, how do you see the RISC-V architecture is going to play the role, and what are the workload they can essentially get a huge benefit from this open infrastructure coming off?
Okay. I don't know if you know the answer just yet in the industry. There are different CPU cores being used, RISC-V being another one of them. and people are looking at adding AI compute to the different cores, and RISC-V could be another option where you can add more AI compute to the RISC-V SoCs. Um, Maybe to start with, it is more applicable in the edge compute or IoT devices where the compute needs are relatively low, um, and and you can add AI compute core to your RISC-V and bring out a solution targeting um, low power, low compute requirement solutions. But that is just a example, and we really don't know how the industry will shape. I'm sure there will be experiments carried out over a period of next few years to see what CPU architectures and how to pair up the CPU architectures with the AI for the different AI compute needs.
Yeah, thanks a lot, Bharat. Again, I think I do agree with you. It's the another very interesting question, and I know this doesn't have the answer. It's more forward-looking. The question is, what are the major bottlenecks to mimic the human brains with the help of deep learning AI into our SoC architecture? So maybe this is very forward looking. I know it's a
Yeah,
very challenging
yeah,
because if you think through the human brain capacity is worked at equivalent to a 70 millivolt transistor, and with a 12 watt of power what it really can generate, it's a humongous challenges for us to go to that level. It will take decades in my mind, but Bharat, I would request you to share your thought. This is really a question for our future researcher to as well as for us to see how do we go to that space and what are the your thought.
yeah. Like you said, this is in fact very forward looking. um, we are taking baby steps or nano steps towards getting there in a much more slow and steady manner as we try to provide commercial applications with more and more complexity and higher accuracy targeting some of the human efficiencies. So for example, some tasks on image recognition, object detection, there has been uh, breakthroughs where we have been able to match the human level of accuracy on a data set. But that is only in one area, and then humans are capable of doing this at so many different tasks we can't even imagine. There are, from an architecture perspective, there are different approaches being taken. Go down to very low precision arithmetic, improvise our compute, which is a lot more organic, which is, but then we control the destiny, which is in the next 5 years, 10 years. Then there are more bolder approaches, more uncertain of trying to actually mimic the circuits which work like human brain. I think neuromorphic circuits, which haven't seen commercial applications a lot yet, but maybe that is the future. If we can crack it to say how exactly we can mimic. But I don't know if we know enough how exactly the brain works. Um, there are targeted learnings of how the brain works, but getting to the point of performing like a human brain, uh, in my opinion, is decades away, if ever.
Yeah, so the last question, but this is really a forward looking, and I'm sure in this presentations there are a lot of PhD students or the future PhD students, and I would request them to take this challenging field, and we wish that in next maybe 10 years we have a human like small robot which can does and help as a human companion
Right.
devices. That's our wish and pray, and just not that we need to take the engineering responsibility to make that happen. It's a collective responsibility. So one last question, Bharat. This is regarding the the PhD students where they can find out the interesting, challenging problem and which they can work with the ecosystem in India and all over the world. We are in a global village now, where I think my 2 cents to all of my friends who are exploring to do the PhD is basically look at the Google, and you will be finding a tons of interesting problem, as well as you can look at all the AI researcher and see their future research area. That's the very interesting area. And the morning, I think we had a discussions with Professor Helen. That's a good resources as well. So Bharat, maybe you can add your thought process so that our future PhD students can get benefit from this.
Yeah. Like I said, this field is really exploding. Whether you look at from a computer architecture perspective to say, how do we scale the next generation of computer architectures uh, to do the same amount of compute in 1/10 of the power or 1/100th of the power, and whether it is by more efficient data movement or in-memory compute or very high sparse compute or a very low precision compute, so that we get the right mix between accuracy and low compute cost. This is from a computer architecture perspective. Any breakthroughs here can be significant in very near or short term, where you can impact the solutions being deployed today or developed today for commercial applications. Then there is the data science approach to say, how do we bring in a, or research in the areas of different topologies? What should our networks look like so that they have high accuracy or low compute requirement, or they can be deployed for variety of use cases, from natural language processing to vision to recommendation systems or any of the other ones. So there are different network topologies being researched all over the world, not limited to any one country, and also in the industry, different universities and industry. So that's another big area, and any research in that can help bring more solutions or more AI solutions to different problems, whether it is from medical field, security field, agriculture field. You can name it, just about every field you can have an impact with AI, and take baby steps towards bringing more and more human-like compute to our machines. So the problem space, the opportunity is just exponential at this point in the space of AI, whether it is from data science, computer architecture, software on top of software for AI. It's opportunities everywhere.
Yeah, I agree, Bharat. So thank you so much for such a wonderful presentation, as well as very insightful question and answers. And I think I am between your lunch break.
No.
So I let's all have a great lunch, and then be back for the afternoon session. With that, I think we will be going for lunch now. Thanks everybody, and it was a wonderful session. I learned a lot. I'm sure the audience also learned a lot from this session. Thank you so much once again.
And thank you for giving me the opportunity to present, and for all the listeners for tuning in. And if you have any questions or comments, you can reach out to me. And thank you again for the opportunity.